Okay, so now that we've sort of clarified what those three notions are, can we extend any of these to discrete space theories, like a lattice theory, for instance? And why would we be interested in doing that? Well, quantum theory, quantum gravity is likely to discretize space-time somehow.
Okay.
Like, there's lots of different approaches to do that. And more, but one might expect that GR's successor should be background independent, whatever that ends up meaning, right? So we'd be interested in what is a discrete type of background independence. Like, lots of people from loop quantum gravity to causal set theory, these people all would care if we had a good definition of that. And so the question might be, what background structures do lattices introduce if we have a lattice theory? And do lattices always break our continuous symmetries that we might like our theories to have, like translation, rotation, boosts of all kinds? I mean, diffeomorphisms are a continuous symmetry. Are we not allowed to have any of that when we have a lattice theory? To answer these questions, it would be helpful to have a notion of discrete general covariance, right? So the general covariance was writing things in a coordinate independent way. And remember, that exposes background structure and helps us think about symmetries. It doesn't guarantee high symmetry, it doesn't guarantee background independence or whatever, but it helps us to reformulate things in a way that exposes all of that more clearly. And so that's what I'm going to be claiming in this talk, is that we have a good discrete version of general covariance. And it's mostly inspired by the work of Achim Kempf from Waterloo. In these two papers, which I would suggest you read, are very, very interesting. But essentially, what you can do is think of coordinate systems as being essentially the same as a lattice structure. Changing coordinates is basically the same as something called Nyquist Shannon resampling. And writing something in a generally covariant formulation is writing something in terms of a band-limited formulation. But I don't expect you to know what these things on the right-hand side are. And so we're going to have to do a quick review of sampling theory so I can make all this more precise. So sampling theory has to do with band-limited functions. And a band-limited function is one whose Fourier transform has compact support. That would be if your function is band-limited with some bandwidth k, if and only if the Fourier transform of that function has support only for wave numbers k less than k. So it's only within this box of size capital K around 0 that we have support. And the Nyquist-Shannon sampling theorem tells us that we can exactly reconstruct any band-limited function, knowing only its values in a sufficiently dense set of sample points. This is a really magical thing, if you ask me. And so let's show how exactly that's supposed to work. Suppose that we know the values of this function fn at some points xn, which are regularly spaced, xn equals na. So some spacing a, we know the values of the function at those points, and we know that f is band limited with some bandwidth k. In the following reconstruction, where we take these function values, multiply them by these s functions, which are sinc functions, that's sine of x over x, and then shift them around a bit. And so we could do this reconstruction, and this turns out to be exact, no question mark, just equals, when our sample points are sufficiently dense. Here meaning that the lattice spacing is less than some critical lattice spacing, which is pi over the bandwidth. All right, so that's a bit abstract. Let's see a particular example or two of how that works. So consider some function here, which is just a function I've made up, and it has a bandwidth of k equals pi. So critical lattice spacing of a star equals 1. So we can recover this function exactly, knowing only its values at these half integer locations. So it's 0 and 1/2 and 1 and 3/2 and so on, out to plus and minus infinity. So if you know all of those values, what you do is you associate with each position a shifted and rescaled sinc function that matches at the point, and it's 0 at all the other lattice points. So you find the sinc function which does that, and you do that for every point, and then you add those all together, and this gives you back the original function with no approximation at all. Right. So that's a pretty magical property that these band-limited functions have, but it works with less space between our lattice points. Right. So we oversampled in the previous one. We can drop a down to b a star is equal to 1, and just for generality, I've shifted everything by 1/3. Right. Right? So we can do any uniformly spaced lattice, even if it's offset from 0, with the critical spacing here. You do the same sort of thing, find sinc functions for all of them, and add them all together, and there you have back the original function with no approximation. So what we're able to do is we're able to reconstruct that from any sufficiently dense uniform sampling, just from the fact that it's band limited. But the real magic of sampling theory is that we can also recover this function from any sufficiently dense non-uniform sampling. And let's see how that works, because this really is magical. I still don't, like, I absolutely believe it because I've seen the proofs and all of that, but it's just something crazy to me. So consider this the same function, but oversampled 4 times too much, let's say. So with a equals 1/4. So we don't need all of these sample points to reconstruct the function. Actually, we only need about 1/4 of them. We could keep this one, drop this one, drop this one, drop this one, keep, drop, 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 keep. Okay. But there's no reason we have to drop them uniformly, the ones which we keep. So if you throw away 3/4 of the sample points randomly, sort of, you'll find a non-uniform sampling like this, and you can still do a reconstruction from this. And the reconstructions for each of these sample points are now more complicated, but they still have the property that they're 0 at all the other points and that they match at this point. And actually, if I told you, find me a function with 0 at all these locations and which has a value of 1, let's say here, and I asked you to write down that function, this g is basically the function you would intuitively write down. But you do that for each of the points, and then you add them all together, and this gives back the original function with no approximation, as long as the lattice points are sufficiently dense, and whatever that ends up meaning. Like, sufficiently dense has a technical definition, but I'm not going to get into it here. And remarkably, the exact same story is true in higher dimensions. So in particular, think about J1 is the first Bessel function, and R here is a radius. This function is band limited with the square of with the sum of the squares being less than pi for the wave numbers in each direction, right? And so all of the following figures I'm going to show you are equivalent ways to represent FB. They have all the same information, and you can reconstruct each of them from the others. So here you could just plot the function FB. And so here's what I'm going to call the band limited representation of that function. But you could also sample it at every half integer in both directions. So this is an oversampled representation of that function. And just by multiplying these by sinc functions and adding them together, you can get back the original function. And you can do critically sampled square representation, where you sample at every integer location. And it's integers in this case because the band limit was pi, like I mentioned earlier. Anyway, you could rotate your lattice points, right? And this is still a sufficiently dense sampling, which you could use to get back your function. You could sample it on this hexagonal grid if you like. That's fine. This is still enough to get back the original function with no approximation. And you can even do it on a non-uniformly sampled lattice, right? So just from these points, if I knew exactly where all these points are and exactly what the function value was at each of these points, I can reconstruct the function with no approximation. Right? So that was a bit of a lightning review of what's going on with the Nyquist Shannon sampling theory. What's remarkable about band limited functions is that they have a finite density of degrees of freedom, right? So if I draw some circle there, I can identify that there's only 100 degrees of freedom inside this box, right? But where exactly are those degrees of freedom? What space points are they associated with? Well, it could be any of them. Like, as long as I pick a sufficiently dense set of them, then it's fine. So these degrees of freedom have no fixed or definite locations in space, which is just really something extremely interesting from a philosophical point of view. And we've got near total freedom in how we pick our sample points. Again, they have to be sufficiently dense, but other than that, you're basically free to pick your sample points as you like. All right, so this was a very quick review of band limited functions in sampling theory. Any questions about this before we merge this with the part 1? No questions? Had everybody seen that sort of stuff before?
I have. I don't know about everybody else.
Right.
I haven't, but it's pretty amazing.
Shannon Nyquist theorem is pretty amazing in itself, and it's the basis of signal processing when you do digital sampling.
Right.
And you can actually store in ones and zeros a waveform, exactly. Well, a waveform when assuming that you can hear it, right? Because the human hearing is band limited. Therefore, anything that you can hear, I can get into digital sampling and reproduce the waveform exactly. You will not be able to tell the difference. So all those people that say, oh, analog systems are better to store music than digital systems, they just don't know math.
That's right. Yeah, that's exactly right. But band limited functions have a lot of weird properties. They can't be compactly supported in space.
Right.
If they're compactly supported in Fourier transform. So while what Eduardo said is true, that if you only have a band limited hearing capacity, right, then you can take your songs and band limit them, and you would never notice the difference. And then you can just record the values of all the notes at each discrete time step, and then that would give you enough information to do it. But the song would have to be infinitely long.
That's correct.
If you were to do that exactly. But so there's some compromise between doing a cutoff in space and in frequency, and you can do both of those without the human being able to really tell. So it's a little bit more complicated than that, but
it is
very interesting stuff.
When Achim gives his talks, oftentimes about the applications and so on, sometimes I wonder to what point actually you can really apply it physically, because some of them are heavily reliant on the fact that you need extremely delocalized stuff. Like the tails are important in these cases. Right. So it's not trivial when you can actually cut off those tails, right? When you can actually talk about the localization of the signal that you're talking about.
Right. Yeah, there's lots of technical details here, but everything I've said so far is true and applies pretty generally. Okay, so let's move on to part 3.